everyone. One of the topics that we talk about in Chapter 13 is sampling distributions of proportions. So in this video, I have an applet on the left that's going to allow me to take a whole bunch of samples, all of the same size, and then plot the sample statistic. So first I want you to notice that the population proportion is 0.6. So I'm going to write that on my little sheet of paper here. So the population proportion, which we denote as P, equals 0.6. Now, I'm going to do this twice. The first time, I want all my samples to have a size of 100. So we denote sample size with n. So I'm going to let n equal 100. So if I take one sample, size 100, and I calculate the sample proportion, I got a sample proportion of 0.59. Let's do it again. Now I got a sample proportion of 0.63, 0.54, another 0.59, 0.61, 0.58. Notice that none of these samples has actually given me a proportion of 0.6. They're close, but they haven't equaled the population proportion of 0.6. And remember that that's what a sample tries to do. A sample tries to predict what is happening to the entire population. So the samples are close, they're getting there, but they're not quite exactly what's happening with the population. It doesn't mean that there's anything wrong with the samples. This is called sampling deviation, and it's very natural. You saw this when we did simulations. We could have 10 people run exactly the same simulation in exactly the same way, and they would all come up with slightly different answers. So it's perfectly normal and it's okay that this happens. But I want you to see at the very top here, it says that the average sample proportion is 0.59. So even though none of my samples has actually given me the population proportion, the average of all of the samples is getting really close to that population proportion. So let's keep doing this. I want you to see the deviation as it happens. So again, it's kind of bouncing all around 0.6. We got some low ones, some high ones. And again, it doesn't mean that there's anything wrong with these samples. This is just natural sampling deviation. However, take a look at that average sample proportion. Notice now that it's very close to the population proportion of 0.6. Let's see what happens if we take a whole bunch of samples. So now I'm going to generate thousands and thousands of samples and plot the sample proportion for each one of them. So notice that the distribution is unimodal, really close to symmetric, and so it follows this normal curve. And that the average of the sample proportions gave me the population proportion of 0.6. So what does this tell me? This tells me that if I take a lot of samples, even though those sample proportions might not equal the population proportion, the average of all those samples will. So I'm going to use some notation here. The average of the sampling distribution of sample proportions is going to equal the population proportion, which is equal to 0.6. Now what about the standard deviation? So notice that in this case, the standard deviation was 0.049. So the standard deviation of the distribution of sample proportions is 0.49. There's actually a formula for this, and it's the square root of PQ over N. So let's calculate that with the P of 0.6 and see if we get 0.049. So the p is 0.6, q is the complement of p, so 1 minus 0.6 is 0.4, and the sample size was 100. Now if you put this in your calculator, you're going to get 0.48989. So something very, very close to 0.049. Now I want to do all of this again and see if anything changes if I have a smaller sample size. So let's reset the samples, and now I'm going to reduce the sample size down to 25. So the second time around here, let's let the sample size be 25. And let's see if anything changes. So again, I'm going to generate one sample. I got a proportion of 0.72, 0.64, 0.84, 0.68. So notice that I'm actually kind of far off from the average sample proportion. But if I keep doing this, notice again that it's hovering around that 0.6. And now if you look up at the average sample proportion, it's 0.6. So it took us a little longer to get there with the sample size being 25, but it still got to where the average sample proportion was 0.6. Now what happens if we take thousands of these? Notice that I still have a distribution that's roughly symmetric and pretty unimodal, so it follows the normal curve. And I'm going to go back to my notation here. The mean of all these sample proportions is the same as the population proportion, which is 0.6. This gave us 0.601, that's okay. But notice that the standard deviation is different. So the standard deviation in this case is 0.097. If we calculate this using the formula, so we'll have 0.6 times 0.4, and now the sample size is 25. So when I divide this by 25, in your calculator you'll get 0.0979797. It keeps repeating. Oh, well, there's a 5 in there, but anyway, this is what you get. Notice that this standard deviation is twice the size of the standard deviation when we had a sample size of 100. So we have smaller sample sizes. The smaller sample sizes didn't prevent us from getting the average sample proportion equal to the population proportion, but it took a little longer to get there, and we had far more deviation in our samples. And that's what the standard deviation tells us, right? How much spread we have in our distribution. So with a sample size that's smaller, we're going to have a distribution that's more spread out. So it's going to be less unusual to get a sample proportion that's further away from 0.6 than if we have a larger sample size. Larger sample sizes will mean we have less deviation, meaning we'll hover around that 0.6 far closer, and therefore kind of honing in on that average sample proportion quicker. All right, I hope this helps you understand sampling distributions for proportions.